Hello and welcome to today's webinar on battery selection and system sizing. Today's speaker is Eric Bentsen. He is an electrical engineer and a senior application engineer for Schneider Electric Solar.
Thank you, Sandra. And thank you to everybody listening in on the phone today. Schneider Electric Solar brings a wealth of experience and product knowledge that spans over 2 decades. We're proud to stand shoulder to shoulder with other leading brands such as Square D, APC, and ASCO. Schneider Electric is committed to meeting the needs of the world's energy future with safe, reliable, and intuitive products that have and will continue to stand the test of time. Solar with storage is still in its infancy, and we are here to influence, enhance, and innovate our way toward an exciting future in energy management. Now, more than ever, customers are taking their energy needs into their own hands. There's no reason why a home or a business should be without clean, efficient power for any length of time. Staying digitally connected provides peace of mind, no matter where you are in the world. So we're going to start out with an overview of our family of accessories, as well as our main topic is going to be centered around the XW Pro, battery selection and system sizing. I just wanted to quickly go through the accessories. Our 2 solar charge controllers, the MPPT 60, which is a 60 amp, 150 volt DC max on the PV side. We have an 80 amp controller, which is a high voltage charge controller. It's up to 600 volts DC on the PV side. Our monitoring devices are Conext Gateway with the Cloud Insight 2. And then our battery monitor provides state of charge for the battery that you select to team up with our product. Our balance of systems include the full-size power distribution panel and the mini power distribution panel. Conext configuration tool allows for technical functions and features that are installer related, such as calibration, saving configuration, and things that are more applicable to the installer. Our Disconnect RS is our arc fault rapid shutdown solution for rooftop solar in the US. And then, of course, our automatic generator start module provides automatic starting and stopping of a generator. Specifications for the XW Pro is 140 amps DC, 48 volt battery bank exclusively. DC input range 40 to 64 volts. We offer 3-stage charging, 2-stage charging, boost charging for flooded lead acid battery types. We have external BMS communication capability and a custom battery menu. Our output power is 6.8 kW at 25C. We have a very robust surge capacity, which is 8.5 kW for 30 minutes. And a full 12 kW for 60 seconds. Grid cell power is 6 kW. Frequency selectable, it is a split phase system, 12240. Has a very wide temperature range, -25C to 70C. AC coupling is another feature that's built into XW Pro, and we provide frequency shift regulation. Batteries are central to our battery-based system. Without a battery, the inverter and the charge controllers won't even turn on. The question's always often been asked in the past, well, can I just get the XW now and add a battery bank later? And the answer is no, not if you want it to power on. It requires minimum DC voltage across the terminals to activate the internal circuitry. Low state of charge is not going to be healthy for flooded battery types. State of health is often determined on how the battery is treated. So if you have a state of charge tolerant battery chemistry, then it's going to be more tolerant of partial state of charge, and you're not going to have to worry about discharging it too deeply or leaving it at a particular low state of charge for extended periods of time. Poor battery performance is going to be evident by poor system performance. So when it comes to selecting a battery, you should have a conversation with the customer and educate them as much as possible on the key benefits of certain chemistry. There may be certain things that are the most important to the customer. It could be cost. It could be the number of cycles that the chemistry is good for. They might be concerned about usable depth of discharge. Is it environmentally friendly? That's often a major concern. And then safety is usually at the top of the list. It could be any number of these things or a combination of them that are important to the customer. And there are certain things that should be considered as well for somebody that is trained in different battery chemistries and what their benefits are. So going back to lead acid, they've been around for 150 years or better, very reliable. However, they're heavy. They are dependent on temperature compensation to provide the same level of charge. So in colder environments, current flow is impeded. So therefore, a higher voltage needs to be targeted to obtain the same state of charge. And then, of course, in warmer climates, then the battery voltage has to be decreased to prevent overcharging. Another thing that's exclusive to lead acid chemistries is the 50% discharge limitation. So when you go below 50%, that's when sulfation occurs. That's not such an issue if you have flooded batteries because you can equalize them to recover their performance. However, they're not as efficient as other chemistries as well. So you're going to get more losses when you're charging and discharging a lead acid chemistry. Lead acid batteries are typically limited in their ability to accept higher charge rates. For example, flooded batteries can typically accept C over 5, whereas sealed lead acid can accept C over 3 or even C over 2 in some cases. For example, a flooded battery rated at 400 amp hours may typically accept only 80 amps of charge current. It's important to calculate PV watts to determine how much current may be supplied to the battery in a backup mode. Assume no AC loads. For example, the customer is away on vacation. Lack of regulation when AC coupling may result in a reduced life cycle of lead acid batteries when the application does not provide a regular 3-stage charge. Some battery warranties are contingent on the batteries receiving a full charge regularly. Lead acid batteries work well in grid-connected AC-coupled applications, especially if used as a standby battery. When cycling the batteries daily, for example, in time-of-use applications, it's important not to allow the batteries to discharge less than 50%, especially if they're sealed. Flooded batteries are more forgiving because they can be equalized to recover their performance. Lead acid batteries are only good for approximately 1,000 cycles and only if they're not misused. So here we see load versus no load hysteresis of a typical lead acid battery. So in bulk, the max charge rate is supplied to the battery until the bulk voltage is reached. At that point, the natural return resistance of the battery requires less and less current to hold the batteries at the bulk voltage. Once the charge current drops to 2% of your declared battery capacity, and that's a settable parameter in our inverter and charge controllers, the charger exits the absorption stage, either to float, as in the case with the MPPT charge controller, or to no float with the inverter charger, assuming a grid interactive application. Notice the significant voltage swing from loaded at approximately C over 10 to charging at C over 3, almost a 9-volt difference. It would be difficult to approximate state of charge from voltage alone, although the state of charge is fairly linear. You can see in the yellow where the discharge is linear but more gradual, while the higher charge rate has a much steeper slope. So lithium iron phosphate is probably, I would say, overtaking lead acid, at least the number of applications that I see for the most part, are specifying lithium iron phosphate batteries probably 3 or 4 to 1 at this point in time. So gradually they're gaining more and more popularity. In some cases, the cost is at parity with lead acid if you consider the number of cycles. So you might replace a lead acid battery up to 3 times in the lifespan of a single lithium iron phosphate bank. 48 volt systems are safer than high voltage lithium packs, offer greater flexibility and expandability, stackability. I've seen lithium banks quite large with 48 volt systems. They're all going to have a built-in BMS, whether they have communications or not with external devices. They have a greater energy density, so that means they'll pack more power with lighter weight. They are state of charge tolerant, so you can leave them at a partial state of charge for extended periods and not that won't be detrimental to the state of health of the battery. They are more efficient battery chemistries than lead acid. They are maintenance free as well, and they offer up to 6 times more cycles than a lead acid battery. Here we see a charge discharge curve for lithium iron phosphate. So notice you've got the voltage climbs very quickly from 0 to 10%, and then again from 95 to 100% when you're charging. And then likewise, when you're discharging, the voltage drops very quickly from 100 to 95%, and then it flattens out. And then from 10% to 0%, it drops out very quickly. So, how would you approximate state of charge from voltage alone? It's really very difficult to do. Note how little the voltage varies from 20 to 80%. It's almost flat. Notice there's only a difference of about 2 volts when charging at C/2 and discharging at the same rate. If the charge-discharge curve for lithium iron phosphate was linear, it would be much easier to approximate state of charge from voltage. Unfortunately, the voltage is almost flat, between 20 and 80%, making it very difficult to approximate state of charge from voltage alone. So when you're using our battery monitor or a SAN bus compatible battery such as Discover, state of charge control is a feature that's exclusive to XW Pro. And this is really huge because of the fact that we just talked about the voltage control is really not very accurate when we apply it to lithium chemistry. So state of charge control allows the user to prioritize stored energy in an AC coupled or a DC coupled system. Battery monitor, Discover, or integrated battery monitor system can provide state of charge data to the XW Pro. Does anybody remember the Trace SW? It had a LBX mode. That meant low battery transfer. That feature allowed customers to remain connected to the grid, but draw virtually nothing from the grid. So, but they didn't have state of charge control back then. This was accomplished by opening the grid transfer relay. The XW Pro can actually stay connected to the grid and draw virtually 0 to support the load by enabling cell mode and set the max cell amps to 0. You can see the power coming out of the battery and just charging to support your backup loads, drawing virtually nothing from the grid. Here's the actual power flowing with a 1400 watt microwave and other household loads. Note 0 power is being drawn from the grid. Note how the XW Pro prioritizes battery power down to grid support state of charge, and the recharge state of charge triggers a charge. So I can discharge my batteries and support the load completely on battery. And then when I get down to recharge state of charge, it'll start a new charge cycle. I can use charge block to block charging during the more expensive periods and charge when the rates are lower. So therefore, you can do arbitrage that way. You can export power during a certain period with the cell block function to minimize loads that are occurring during a specific period of time, or you can even export power back toward the main panel during that specific period of time. So you have a lot more options available to you with the Pro and state of charge control. Note that the charge block feature will block charging during the periods when the rates are higher. The usefulness of state of charge cannot be underestimated. It allows depth of discharge to be very precise, contributing to maximize battery life. In fact, you could disable the charger and wait until DC coupled solar charges the battery to a desired state of charge. It doesn't need to be a full charge either. You could choose to export back to the main panel down to a particular state of charge during a specific block of time. These are screenshots of real power that I logged with my system. So now shifting to application. So when we're designing a system, the goal of the customer should be recognized early in the design phase, which will determine the delta of daily storage requirement. If a customer merely wants to support the loads during solar hours and sell any excess, then the batteries can remain full. The days of autonomy should be considered if it's significant to the customer, typically more important in regions that are susceptible to storms in the United States. If a customer wants to go off-grid, then cycling of the battery should be expected. Targeting state of charge percentage has been made easy with the Conext battery monitor and the Conext AGS. Typically, when we're looking at designing a system, we start with the AC load. So most are going to want to back up certain loads, although it's possible to back up the entire house, and many people do that, but that's going to require a larger system. So when we talk about maximum continuous loads, we also need to consider the surge requirements as well. Assess the power in terms of kilowatt hours for battery bank sizing. Whether designing an AC coupled system for new construction or as a retrofit, it's important to understand how the system will be used and follow certain basic sizing guidelines. We always start with the AC load. This is how to size the inverter charger system. Make sure the customer understands that higher demand, such as air conditioner, electric range, will require a larger system. So you might want to have a conversation. Are you sure you want to back up that range or that electric dryer? In other words, will a microwave do in an outage? Or could you get away with maybe hanging your clothes up? If the outage is rare and of short duration, they might be willing to do that. Otherwise, they're going to have to size the system up, and that's going to be more expensive. So when we're sizing for the storage for on-grid, the requirements can really vary. Are they on time of use or not? Do they desire a certain number of days of backup or days of autonomy? Or are they just concerned with using stored energy to lower their electric bill? For off-grid, you're going to likely need to be more precise in your calculations unless you have a backup generator. If you do have a backup generator, then if you undersize the system, the downside is that the generator will start more often, but it's not the end of the world. If you don't have a generator for backup, then you really need to be accurate in your load assessment as well as your energy assessment so you can properly size the system. Make sure you consider the maximum allowable depth of discharge according to the battery manufacturer. For example, if you figure you need 400 kilowatt hours of backup and you choose a lead acid battery, then you're going to need an 800 amp hour bank because you're only allowed 50% discharge under most conditions. You can discharge lower than that, but if you do so continually, then you're going to need to equalize if they're a flooded battery. If they're sealed, then that sulfation may not be recoverable. Make sure the battery bank is sized to accommodate the total PV. That's important because if you're AC coupling, say the customer goes on vacation and there's an outage, then virtually all of that PV power is going to be pushed into the battery. So that battery must be sized to safely accept that total amount of PV. Likewise, if you're DC coupling, some people even choose to AC couple and DC couple. So you need to consider all of your charging sources and make sure that that amount doesn't exceed the manufacturer's recommendation for maximum charge rate for their battery. So sizing for PV, that can have a lot of different variables. It, could stem from, maybe you have limited roof space. If you have ground mount, that's not going to be an issue, but typically you want a south-facing array if you're in the northern hemisphere, if you can help it. That's not always possible with different facing angles of roof space. And then, of course, if you do have different angles, you're going to need to make sure that you're not running a single controller using different facing strings, because that's not going to be very efficient. You might want to look at microinverters AC coupled for something like that, or module level power electronics that use optimizers. Calculate the kilowatt hours that you're going to need, compare it to a solar insolation map for the region that the system is going to be located. And of course, make sure the battery bank is sized to accommodate a total PV. Here you can see an example of a solar insolation map for Huntington Beach. Well, I lived there for a few years. Now I'm in the Seattle area, and the insolation here is less than half in the winter months, and it's maybe 80% of what you see here in the summer months. So you're going to need to, and again, this might be a limitation according to roof space, but if you're trying to design a particular amount of PV to reduce the draw from the grid commensurate with the load demand, then you need to take these considerations into account. So for residential, for example, knowing the solar insolation is going to allow you to obtain a fairly close approximation of the energy. If shading is an issue, then software is available to model the production more accurately.